From International Journal of Heat and Mass Transfer, Elsevier. Flow and heat transfer characteristics of single jet impinging on protrusion surface. By D. Zhang, Huancheng Ku, Jibing Lan, Jianhui Chen, Yonghui Xie. Stagnation Nusselt number. Figure 1 shows the stagnation Nusselt number distributions of impinging jet on protrusion target surface with the change of jet Reynolds number. The stagnation Nusselt number distributions on smooth target surface by literature, 26, 29, are introduced in the present numerical study for comparisons. The correlative expression are given by Tarikov et al. Nu 0 equals 1.24 pr to the power of 0.33 re to the power of 0.5 L by dj to the power of minus 0.11. While the expression by Li and Li, Nu 0 equals 0.433 re to the power of 0.565 L by dj to the power of 0.0384. Tarikov and Li adopted different experimental details to obtain the correlative expressions. A certain deviation exists in their expressions. Based on the present study, a correlative expression of stagnation Nusselt number between Nu 0 and d, Re, dj, d is given below. Nu 0 equals a 0 ray to the power of a dj by d to the power of beta delta by d to the power of gamma, where a 0 equals 1.4069, alpha equals 0.5116, beta equals 0.1347, gamma equals 0.1388. The mean square deviation is 2.72%. The variation of stagnation Nusselt number is obtained through the coefficients in the above correlative equation and the figure. Stagnation Nusselt number is higher with larger protrusion relative depth, jet to protrusion diameter ratio and jet Reynolds number. Furthermore, stagnation Nusselt number on target surface with protrusion is higher than that on smooth target surface. The distance between protrusion dome and impinging jet nozzle gets smaller when the protrusion relative depth increases, so the heat transfer in the stagnation is improved significantly. Average Nusselt number of protrusion. The averaged heat transfer characteristics of impingement target surface are more concerned. The average Nusselt number. Nu average is defined by Nu average equals sigma nu I dsi by sigma dsi multiplied by sigma dsi by sigma dpi, where nu I is the local Nusselt number of every element on the protrusion surface, dsi and dpi are the protrusion element surface area and corresponding projected surface area, respectively. This definition of average Nusselt number takes the heat flux brought by additional area of sphere comparing with flat surface into account. For more convenient comparisons, the average Nusselt number of impingement on flat plate with comparable areas is given. Figure 2 presents average Nusselt number distribution on the protrusion surface with the change of jet Reynolds number. Average Nusselt number for smooth target surface with corresponding areas is also given for comparison. Based on the present numerical results, a correlative expression of average Nusselt number on protrusion surface Nu average between delta by d, Re, dj by d is obtained. Nu average equals a 0 Re to the power of alpha dp by d to the power of beta delta by d to the power of gamma. Among them a 0 equals 1.5325, alpha equals 0.4864, beta equals 0.2873, gamma equals 0.1335, the mean square deviation is 4.78%. The variation of average Nusselt number on protrusion surface is obtained and it is summarized as below. The variation of average Nusselt number on protrusion surface is the same with that for stagnation Nusselt number. In detail, Nusselt number is higher with larger protrusion relative depth, jet to protrusion diameter ratio and jet Reynolds number. However, it is worth pointing out that average Nusselt number on protrusion, when dj by d equals 0.318, 0.5 and delta by d equals 0.1 has slight difference with that for corresponding smooth target surface. The average Nusselt number of protrusion except the above case is higher than that of smooth target surface. For further deduction, the overall improvement of heat transfer for most cases is obtained by the heat transfer enhancement in stagnation region and the increase of protrusion sphere area. Conclusions. The flow characteristics of a single jet impinging on a protrusion surface were investigated using PIV and numerical simulations. and the heat transfer characteristics were explored on the basis of the numerical results when dJ by D equals 0.318, 0.5, 1.045. Delta by D equals 0.1, 0.2, 0.3 and Re equals 5,000, 10,000, 23,000 for the first time. The detailed conclusions are drawn as follows. Flow structures of impinging jet on protrusion target surface are not sensitive to protrusion relative depth and impinging jet Reynolds number. The jet turns its flow direction as it impinges onto the protrusion. Then the flow separation occurs when flow passes through protrusion edge region and at the same time secondary impinging jet forms. The wall jet continues to develop along the radial direction after apart from the edge of the protrusion. According to the characteristics of pressure coefficient distribution when dJ by D equals 0.318, the flow of single jet impingement on the protrusion target can be divided radially into 4 different regions: stagnation region, wall jet region 1, protrusion edge region, and wall jet region 2. Wall jet region 1 gets smaller with the increase of dJ by D. The protrusion is covered by impinging jet stagnation region completely when dJ by D equals 1.045. The local Nusselt number on the protrusion surface is higher in the comparison with smooth surface on the whole, and the local Nusselt number increases with the protrusion relative depth. However, local Nusselt number decreases with the increase of protrusion relative depth when the wall jet passes into protrusion edge region. Local Nusselt number drops firstly and then increases. Drops again in protrusion edge region, so the peak value emerges, which can be explained clearly by the secondary impinging jet concept proposed in the present. The local Nusselt number recovers to the same level with that of smooth target surface after passing through protrusion edge region, and decreases gradually as flow develops. Based on the numerical results, the correlative expression of stagnation Nusselt number between nu0 and delta by D, Re, dJ by D is obtained. Stagnation Nusselt number increases with the increases of protrusion relative depth and jet Reynolds number, and stagnation Nusselt number on protrusion target surface is larger than that of smooth target surface. Based on the numerical results, the correlative expression of average Nusselt number between nu0 and delta by D, Re and dJ by D is obtained. It takes both the decrease of the local Nusselt number after arranging the protrusion and the increase of the heat exchange area into account. The average Nusselt number increases with the increase of protrusion relative depth and jet Reynolds number. The overall improvement of heat transfer for most cases is obtained by the heat transfer enhancement in stagnation region and the increase of protrusion sphere area.